That's Claire here for Claire Maths. Today we're going to look at whole logarithms for the Higher Maths 2023 exams. This includes evaluating numerical expressions, logarithmic equations, exponential equations, looking at the graphs of logs and exponentials, and of course, looking at finding the logarithmic relationship from straight line graphs when you change the axes to logarithmic axes. Let's get started. Okay, evaluating numerical expressions. SQA Higher Maths 2015, paper 1, question 6. Evaluate log 612 plus a third of log 627. So I'll keep the log 612 to start with, but then I'll write that as plus of log 627 to the power of 1/3, because we can take that up. So that's log 612 plus 27 to the power of 1/3 is the cube root of 27, which is 3. So log 6(3). And then adding logs means we can just time it into one log and the numbers times together. So that's log 6 of 12 times 3, that's log 636, which is equal to 2, and that's because, remember, 6 squared equals 36. So 2 is our final answer, and we're done there. Evaluating numerical expressions for logs, SQA Higher Maths 2016, paper 1, question 14. Part A, evaluate log 525, 2, because remember that means 5 squared equals 25. It's as simple as that. Part B, hence solve log 4x plus log 4x minus 6 equals log 525. So looking at our left-hand side, we combine that into one log by saying that it's x times x minus 6. So I'll do that to start with, log 4x bracket x minus 6. And the right-hand side, log 525, well, we know that's 2, so we can just write 2. So then we can use our rules of logs to say that it's a base to the power of 2 equals the left-hand side. So in other words, 4 squared equals x times x minus 6 to eliminate the log. Now we're just going to get a quadratic. 16 equals x squared minus 6x. Moving over to the same side, you get x squared minus 6x minus 16 equals 0. So you've got a quadratic to solve. Hopefully that's factorizable. X and x. 8 and 2, minus 8 plus 2, because minus 8 plus 2 is minus 6, minus 8 times 2 is minus 16. So that gives me x equal to minus 2, or x equal to 8. But x equal to minus 2 is not a valid answer, because the log of 0 or anything negative is undefined, so x has to be greater than 6. So we can just score that out and say that x has to be greater than 6 is the answer. So our final answer is x equal to 8. And we're done there. Okay, evaluating numerical expressions, SQA Higher Maths 2018, paper 1, question 6. Find the value of log 5250 minus a third of log 58. So we're going to combine these. So we'll keep the log 5250 hanging out for a minute, but we can say minus log 5, 8 to the power of a third, because you can take coefficients up as a power. We'll work out that 8 to the power of a third then, so that's log 5250 minus, remember, to the power of a third is the cube root, so it's log 52. And now we can combine a minus, because a minus means you can do this number divided by this number. So as one log, we get log 5, 250 over 2. That's log 5, 125. So 5 squared is 25, so 5 cubed is 125, so the answer is 3, because 5 cubed is 125. And we're done there. Okay, evaluating numerical expressions, SQA Higher Maths 2019, paper 1, question 14. Part A, evaluate log 10(4) plus 2 log 10(5). So we've got log 10(4) plus log 10(5) squared, because I can take the 2 up. So that's log 10(4) plus log 10(25). And then we can combine that because we can times the numbers together. So it's log 10(4) times 25, which is log 10(100). Log 10(100) is equal to 2, because 10 squared equals 100. And there we are. Part B. Solve log 2 7x minus 2 minus log 2 3 equals 5. So we'll combine that into one log straight away by writing log to 7x minus 2 all over 3, because a minus means we can divide. And that equals 5. So when using our rules of logs to eliminate, we've got a log on one side and a number. So 2 to the power of 5 equals this. So I can write that 2 to the power of 5 is 7x minus 2 over 3. So we need to work out 2 to the power of 5. Well, 2 twos is 4 times 2 is 8. Times 2 is 16. Times 2 is 32. So we get 32. So 32 equals 7x minus 2 over 3. So we can times 32 by 3. 32 times 3 is 96. So 96 is 7x minus 2. Add 2 to both sides. So 98 is equal to 7x. Dividing through by 7 then, you get 14 equals x, or nicer, x equals 14. And we're done there. SQA Higher Maths 2022 Paper 1, Question 2. Evaluate 2 log 3x minus log 3/4. So it's just a 3-mark question, this one. The first one we're going to apply is the idea that 2 log 3/6 can be simplified to log 3/6 squared. So you get your first mark for simplifying this first log to log base 3 of 6 squared. And we can still write minus log base 3 of 4. As long as you wrote this, there's your first mark there. And then our second mark for combining the takeaways into one log as a divide. In other words, log base 3 of 6 squared over 4. There's our second mark there. Let's just take a note of that. And of course our third mark for then evaluating what that is, so working it out. So let's do some work on that. Log base 3, 36 over 4 equals log base 3 of 9. Well, 3 squared is 9, so log base 3 of 9 equals 2. And there is our final mark right at the end for getting 2. Just a little note on this. If you did the correct answer but did no working on this question, you would get no marks. You have to show your steps to show that you understood it. Otherwise, the SQA just thinks you were guessing on this question. Evaluating numerical expressions for logs, SQA Higher Maths 2016, Paper 1, Question 14. Part A, evaluate log 5/25, 2. Because remember that means 5 squared equals 25. It's as simple as that. Part B, hence solve log 4x plus log 4x minus 6 equals log 5/25. So looking at our left-hand side, we combine that into one log by saying that it's x times x minus 6. So I'll do that to start with. Log 4x bracket x minus 6. And the right-hand side, log 5/25, well, we know that's 2, so we can just write 2. So then we can use our rules of logs to say that it's a base to the power of 2 equals the left-hand side. So in other words, 4 squared equals x times x minus 6 to eliminate the log. Now we're just going to get a quadratic. 16 equals x squared minus 6x. Moving over to the same side, you get x squared minus 6x minus 16 equals 0. So you've got a quadratic to solve. Hopefully that's factorizable. X and x, 8 and 2. Minus 8 plus 2, because minus 8 plus 2 is minus 6. Minus 8 times 2 is minus 16. So that gives me x equal to minus 2 or x equal to 8. But x equal to minus 2 is not a valid answer because the log of 0 or anything negative is undefined. So x has to be greater than 6. So we can just score that out and say that x has to be greater than 6 is the answer. So our final answer is x equal to 8. And we're done there. Solving logarithmic equations, SQA Higher Maths 2017, Paper 1, Question 12. Given log a 36 minus log a 4 equals a half, find the value of a. So these are rules of logs to combine the logs. So that can give me log base a, and we've got 36 divided by 4, because of a minus, equals 1/2. So log base A, 36 divided by 4 is 9, equals a half. So eliminating the log, A to the power of a half equals 9. A to the half equals 9. So that means the square root of A, we could write that, I suppose, equals 9. So if I square both sides, A equals 81. And we're done there. Solving logarithm equations, SQA Higher Maths 18, paper 1, question 11. Diagram shows log 3x. On the diagram in the answer book, sketch the curve with equation 1 minus log 3x, and then find the point of intersection between the curves, which will be solved with logarithmic equations. So 1 minus log 3x, the minus part here tells me to reflect in the x-axis, and then the 1 part, which I'll do in another colour here, tells me to then move up by 1. So first of all, reflecting on the x-axis, this point will stay where it is, but this point will jump down here, and that would be at the moment as in point 3 minus 1. But now I have to move up by 1, so this point is going to jump up by 1, so that becomes 1, 1. And you can see this point goes up to 3, 0. So I can just write the number 3 here. Getting rid of my intermediate working, which you could use a rubber if you were doing this by hand. And since it's reflected, it's going to go down and through here. So we can just draw that in, down here, through the way, and there we go. It's a reflection in the x-axis. Okay, part B, determine the exact value of the point of intersection, simultaneous equations. So for part B, we've got y equals log 3x, but we've also got y equals 1 minus log 3x. So we can say that they are equal to each other and find x. So log 3x equals 1 minus log 3x. So taking the log 3x to the other side, you'll have log 3x plus log 3x. So 2 of them, 2 log 3x equals 1. I can take the 2 up as a power, so I get log 3x squared equals 1. Now I've got it in the form log of something equals a number, so 3 to the power of 1 equals x squared. 3 to the power of 1 equals x squared, and therefore I can find x. X equals 3 to the power of a half, or x equals the square root of 3. And we're done there. Notice it'll only be the positive part of this instead of the negative part, because if x was negative, then you would have log of a negative number, which doesn't exist, so it's just a positive. I can take a note of that. Just positive value, as x has to be greater than 0. Okay, evaluating numerical expressions, SQA Higher Maths 2019, paper 1, question 14. Part A, evaluate log 10 4 plus 2 log 10 5. So we've got log 10 4 plus log 10 5 squared, because I can take the 2 up. So that's log 10 4 plus log 10 25. And then we can combine that because we can times the numbers together. So it's log 10 4 times 25, which is log 10 100. Log 10 100 is equal to 2 because 10 squared equals 100. And there we are. Part B. Solve log 2 7x minus 2 minus log 2 3 equals 5. So we'll combine that into one log straight away by writing log 2 7x minus 2 all over 3, because a minus means we can divide. And that equals 5. So then using our rules of logs to eliminate, we've got a log on one side and a number. So 2 to the power of 5 equals this. So I can write that 2 to the power of 5 is 7x minus 2 over 3. So we need to work out 2 to the power of 5. Well, 2 2s is 4 times 2 is 8. Times 2 is 16, times 2 is 32. So we get 32. So 32 equals 7x minus 2 over 3. So we can times 32 by 3. 32 times 3 is 96. So 96 is 7x minus 2. Add 2 to both sides, so 98 is equal to 7x. Dividing through by 7 then, you get 14 equals x, or nicer, x equals 14. And we're done there. SQA Higher Maths 2022 Paper 1 Question 8. Solve log base 6x plus log base 6x plus 5 equals 2 where x is greater than 0. So a couple of different methods you could have used here. So I'll go through the alternatives for you. Let's call this one method 1. And the first method is to combine the two logs. The plus is one single log. So we could write that as log base 6 of x times x plus 5 equals 2. And there's your first mark there. Okay, moving to the second mark, we can write that as 6 squared equals x times x plus 5, or x times x plus 5 equals 6. So there's our second mark there. And then we can move on to try and solve that as a quadratic equation. So standard quadratic way, multiply out the brackets, we get x squared plus 5x, and that equals 36. So tidying that up, minus 36 equals 0. There's our third mark there for putting it in the proper quadratic form. And then our fourth mark, try to solve that. Double brackets, x and x, 9 and 4 times together to make 36, but take away make 5. So we've got plus 9 minus 4. So x equals 4 or x equals minus 9. But x has to be greater than 0 because it says so in the question. So we disregard one of the answers. So since x is greater than 0, x equals 4 is the only valid answer. And there is our final mark right there. We have to have stated that x equals 4. We disregarded the minus 9 to get that final mark. Let's look at method 2. So method 2 starts the same way. We apply the same rule as before. So we write log base 6 of x bracket x plus 5 equals 2. And we get our first mark. The log base 6 of x plus 5 equals the log base 6 of 6 squared. Because remember, log base 6 of 6 is 1, so that is 2. And that would give us our second mark. And then we can cancel the logs from both sides to just write x plus 5 equals 6 squared, or x squared plus 5x equals 36. And it continues in the same way as the last method. Minus 36 is 0. There's our other mark. And then for our final mark, solving that equation, we get x and x, 9 and 4, plus 9 minus 4 equals 0. So x equals 4 or x equals minus 9. But since x is greater than 0, x equals 4 is the answer. And there's our final mark there. For 4 marks. Solving exponential equations, SQA Higher Maths 2016, Paper 2, Question 6, otherwise known as experimental data with exponentials. Scientists studying the growth of a bacteria strain. The number of bacteria given is B equals 200 e to the 107t. State the number of bacteria present at the start of the study. The start means t is 0. You can either remember then that gives you e to the nothing, which is 1, so you get 200, or you can write that out actually. So at the start, t equals 0. So b of t equals 200 e to the 0.107 times 0. That's 200 times e to the 0, which is just 200. Calculate the time taken for the bacteria to double for part B. So if it doubles, that means that b of t becomes 400. So I can then write 400 as our b equals 200 e to the 0.107t was our equation. And we need to solve that. So divide by 200. 400 divided by 200 is 2, which is what you should get, e to the 0.107t. Now we can take the log of both sides, the natural log, so log 2 or log e2 equals log of e to the 0.107t, or if you prefer log e. Taking it down as a power, so you get log 2 equals 0.107t times log e of e, which is just 1. So log 2 equals 0.107t. Divide through by 0.107, t equals log 2, divided by 0.107. Get your calculator out and you will get about 6.48. So 6.48 hours, because hours was our unit of time. Solving exponential equations. SQA Higher Maths 2018, Paper 2, Question 11. A supermarket has been investigating how long customers have to wait at the checkout. During any half-hour period, the percentage of customers who wait less than t minutes can be modelled by this equation. P equals 100 times 1 minus e to the kt. Part A. If 50% wait less than 3 minutes, determine k. So I've got two values that I can just substitute in. So for part A, P equals 100, 1 minus e to the kt. So 50 is our percentage, equals 100 times 1 minus e to the power of 3k, because t is 3. Multiplying the bracket out, we get 100 minus 100 e to the 3k. So we can take the 100 over. 50 minus 100 is minus 50, equals minus 100 e to the minus 3k. Dividing through by minus 100, minus 50 over minus 100 equals e to the 3k. Well, that's a half, so that's 0.5 equals e to the 3k. You could have actually divided by 100 at this point here to get the half, worked it from there, but you get the same answer. Take the log of both sides. Natural log of 0.5 equals the natural log of e to the 3k. So the natural log of 0.5 equals 3k times the natural log of e. So that means that log of 0.5 equals 3k. So k is the log of 0.5 over 3. And we can work that out as a value in our calculator. You get minus 0.231. And we're done there. Part B says calculate the percentage of customers who wait 5 minutes or longer. So t is just 5. P is 100, 1 minus e to the minus 0.231 t, because k is minus 0.231. So when t is 5 minutes, p equals 100 times 1 minus e to the minus 0.231 times 5. And then we just need to work that out. If you do that in a calculator, you'll get 68.5. So it's 68.5%. Wait for less than 5 minutes. Because remember, this formula is for the number of percentage of customers that wait for less than a specific time. So that means that for those who wait 5 minutes or longer, which is what the question is, I just do 100 minus 68.5, which is 31.5%. Wait for 5 minutes or more. And we're done there. Solving exponential equations, SQA Higher Maths 2019, Paper 2, Question 9. Electricity on a spacecraft can be produced by a type of nuclear reactor. The electrical power produced by a generator is PT equals 120e to the minus 0.0079t. Don't be put off by this t, it's just part of the symbol to tell you that p is a function of time. Where PT is the electrical power in watts after t years. Determine the electrical power keyword initially produced by the generator. So if it's initially produced by the generator, that means part A, when t equals 0, PT equals 120 e to the minus 0.0079 times 0. Well, that gives you P of t equals 120 e to the power of 0, which is 120, because e to the power of 0 is 1. So we're done there. We could put the units in just to be clear. Watts. Part B, calculate how long it takes for the electrical power produced by the generator to reduce by 15%. So let's reduce this by 15% by doing a little bit of maths. If it's reduced by 15%, there's 85% less. So that means that the power is going to be 0.85 times 120. And you just get a calculator out for that to get 102. So that's our new power. So that means that 102 equals the initial power, 120, e to the minus 0.0079 t. And we're going to solve for t. So it's an exponential equation, so I can divide through by 120 to get 102 over 120 equals e to the minus 0.0079 t. That gives me 0.85 on this side. E to the minus 0.0079 t. And if we're working in percentages, you'll realise that this number here will be basically what the question's asked us anyway, but I always start from here just to be on the safe side. So then we can log both sides using the natural log. The natural log of 0.85, or log e of 0.85, equals the natural log of e to the minus 0.0079 t. Pretty standard stuff. That means that log 0.85 equals, take the power down, minus 0.0079 t times the log of e. The natural log of e is 1, so that means that log 0.85 is just equal to minus 0.0079 t, and therefore t is the natural log of 0.85 divided by minus 0.0079. And we can just get our calculator out and place log 85 over 0.0079, with a minus in front of course, and you'll get 20.6. And the units were years.
Question 10. The heptathlon was an athletics contest made of 7 events. Athletes score points for each event. In the 200 metres event, points are calculated using this formula, where P is the number of points and T is the athlete's time in seconds. Calculate how many points are awarded for a time of 24.55 seconds in the 200 metres event. So we just need to substitute 24.55 in for T. So we've got P equals 4.99087, 42.5 minus 24.55 to the power of 181. That's 4.99087 times 17.95 to the power of 1.81. 929.0368. Let's just make that 929.04. It doesn't quite specify whether it points are whole numbers or not, so that seems reasonable given the accuracy of the rest of the question. Right, in the part B, in the long jump event, points are calculated using this formula, where P is the points, D is the distance in centimetres, and K is a constant. It says 850 points are awarded for a jump of 600, calculate K, so we'll just substitute in and work from there. So we've got P, which is 850, equals 0.188807. D is 600, minus 210 to the power of K. So 850 equals 0.188807, 390 to the K. So dividing through, we get 850 over 0.188807 equals 390 to the power of K. Logging both sides, I'll just use the natural log. Taking the K to the front then. Equals log of 850 over 0.188807 divided by the log of 390. So it's time to get a calculator to work these out. 1.40999, so k equals 1.41.
Logarithmic graphs, SQA Higher Maths 2015, paper 1, question 13. The function f of x is 2 to the x plus 3 is defined on R, the set of real numbers. The graph of equation y equals f of x passes through 1b and cuts the y-axis at q as shown. What is the value of b? Well, it passes through 1b, so I can just sub 1 in. So for part A, we've got f of x is equal to 2 to the x plus 3. So at x equal to 1, we're going to say that f of x equals 2 to the power of 1 plus 3, which is 2 plus 3, which is 5. So just to answer the question, b equals 5. And we're done there. So part B says copy the diagram above and sketch the inverse function and then write down the coordinates of the images of P and Q. What it means by the images of P and Q is what does P and Q become in the inverse function. So this is an exponential, so the inverse function is a log. So we need to reflect that in the line y equals x. So let's just go ahead and do that. So I've copied the diagram below. So we already know that P is 1b, which we've just worked out is 1, 5. And then let's work out our y-intercept for this graph. So that is when x equals 0. So f of x, which was 2 to the power of x plus 3. That's 2 to the power of 0 plus 3. 1 plus 3 is 4. So we get 0, 4. We need to reflect in the line y equals x. So drawing a y equals x sign. So 0, 4 becomes a long 4, 0. And 1, 5 becomes 5, 1. And we've got an exponential curve like so. That's the inverse function of x. So that's part 1 done. And then for part 2, I've already done the work for it. The image of P and Q, we've got 4, 0. And we've got 5, 1. And we're done there. Part C says, R3, 11 lies on the graph of equation y equals f of x. Find the coordinates of the image of R on the graph of equation y equals 4 minus f of x plus 1. So writing down f of x again, f of x, remember, was 2 to the power of x plus 3. And we know that the R lies on this, which is 3, 11. So our new equation is y equals 4 minus f of x plus 1. So what does that mean? Well, let's just take a few notes. In here means we move left by 1. Minus f of x means we reflect in the x-axis. And you can think of this, that's like plus 4, so move up by 4. If it helps, you can rewrite this as minus f of x plus 1, and then add the 4 on the end, and you might be able to see that better. So that means we've got our R, which was 311. So doing the things in the correct order, we apply our reflection, and then we move left, and then we move up. So our reflection minus f of x plus 1, 311 becomes 3 minus 11, because it drops down underneath. And then that goes to moving left by 1, so 3 becomes 2, so 2 minus 11. And then finally, we need to move up by 4, so we get 2 minus 7 as our final answer. Now, if you're really struggling with that, one way to do it is to go back to the original graph and actually draw it, reflect it, move it to the left, move it up, and note that point moving around. Okay, logarithmic graphs, SQA Higher Maths 2016, paper 1, question 10. Diagram below shows the graph of a function log 4x, base 4. The inverse function exists. On the diagram, on your answer book, sketch a graph of inverse function. Okay, I'll just draw you a quick sketch of this. So you've got your y-axis, you've got your x-axis, and you should know that a log graph's inverse is an exponential. It reflects in the line y equals x. So these points, you can just switch the order. So 1, 0 becomes 0, 1, and 4, 1 becomes 1, 4. So I can note 0, 1 on the y-axis, and it was 4, 1, so a long 1 up 4. Let's just draw it there. And there's our 2 points, and then all you need to do is draw your curve. And you can note that that is f of inverse f of x, f of minus 1x. And we're done there. Solving logarithmic equations, SQA Higher Maths 18, paper 1, question 11. Diagram shows log 3x. On the diagram in the answer book, sketch the curve of equation 1 minus log 3x, and then find the point of intersection between the curves, which will be solved with logarithmic equations. So 1 minus log 3x, the minus part here tells me to reflect in the x-axis, and then the 1 part, which I'll do in another colour here, tells me to then move up by 1. So first of all, reflecting in the x-axis, this point will stay where it is, but this point will jump down here, and that would be at the moment as in point 3 minus 1. But now I have to move up by 1, so this point is going to jump up by 1, so that becomes 1, 1. And you can see this point goes up to 3, 0. So I can just write the number 3 here. Getting rid of my intermediate working, which you could use a rubber if you were doing this by hand. And since it's reflected, it's going to go down and through here. So we can just draw that in, down here, through the way, and there we go. It's a reflection in the x-axis. Okay, part B, determine the exact value of the point of intersection, simultaneous equations. So for part B, we've got y equals log 3x, but we've also got y equals 1 minus log 3x. So we can say that they are equal to each other and find x. So log 3x equals 1 minus log 3x. So taking the log 3x to the other side, you'll have log 3x plus log 3x, so 2 of them, 2 log 3x equals 1. I can take the 2 up as a power, so I get log 3x squared equals 1. Now I've got it in the form log of something equals a number, so 3 to the power of 1 equals x squared. 3 to the power of 1 equals x squared, and therefore I can find x. X equals 3 to the power of a half, or x equals the square root of 3. And we're done there. Notice it'll only be the positive part of this instead of the negative part, because if x was negative, then you'd have log of a negative number, which doesn't exist, so it's just a positive. I can take a note of that. Just positive value, as x has to be greater than 0. Logs. Finding the relationship from a straight line. So in other words, changing the axis so that one or both become logarithmic axes, and then that makes a straight line, so we can work from there. So let's have a look at this question. Two variables x and y are connected by the equation y equals k times x to the power of n. The graph of log 2y by log 2x is shown. Find the values of k and n. So you can memorize how to do this, but I usually just start from the beginning, which is to say that y equals kx to the n. If I've got y equals kx to the n, I can log both sides. And the base is 2, so I can say that log base 2 of y equals log base 2 of kx to the n. Separating the product k and x to the n, I can say that log 2y equals, I'll write the x one first, log 2x to the n plus log 2k. So I can then write log 2y equals n comes down, log 2x plus log 2k. And that looks like now y equals mx plus c. That's like your big Y equals, that's like your mx plus c. So our gradient is equal to our n, and our c is equal to our log 2k. So if we can find the gradient, we know our n, and we can find c with where it cuts the y-axis, we know log 2k. So let's look at our graph. So for our gradient, we've got along 12 and up 3 over 12. So our gradient is 3/12. So our gradient is equal to 3 over 12, which simplifies to 1/4, and therefore n equals 1/4. Now to get our c, we know that log 2k is where it cuts the y-axis. Our graph tells us it cuts the y-axis at the number 3. So we're just solving log 2k equals 3. That means 2 to the power of 3 equals k. 2 to the power of 3 equals k. And therefore k equals 8, because 2 cubed is 8. And we're done there. Relation from a straight line for logarithmic graphs. SQA Higher Maths 2019 Paper 2, Question 12. Two variables x and y are connected by the equation, and this is what you're looking for. Y equals ab to the x, a power. And we're looking at one of the axes is logged, but the other one is not. So it's only one log this time. But always start from your equation and get the logs coming out and see where you go. So I'll start with y equals ab to the x. We'll have to find the values of a and b. So let's start with y equals ab to the x. Just log both sides then. Our log base is 4, so looking on our graph, log base 4y equals log base 4 of ab to the x, which is a product, so I can separate that into a plus. So log base 4y equals log base 4 of b to the x. I like the x one first, like mx plus c, plus log base 4a. Taking the x to the front, we get log base 4y. That's a y and that's a log, equals x times log base 4b plus log base 4a. Well, y equals mx plus c is our straight line, so let's put the x on the end so you can really see it. Log base 4y equals log base 4b times x plus log base 4a. So that's like y equals mx plus c. So we can see our gradient is equal to this number in front of x, and our c is equal to this. So we can say our gradient is equal to log 4b. So let's just check our graph to see if we can work out the gradient. We're given 2 points. So our gradient is equal to y2 minus y1 over x2 minus x1. So that's 8 minus minus 1 over 3 minus 0. That's 9 over 3, which is 3. So we know our gradient's 3. So log base 4b equals 3. Remember, that means that 4 to the power of 3 equals b. 4 cubed is b. 4 cubed is 64, and therefore b equals 64. Now let's try our c. From the work we've just done, our c is equal to log base 4 of a. C is where it cuts the y-axis. We know it cuts the y-axis at 0, minus 1, so c is minus 1. So we can just straight away say that minus 1 is equal to log base 4 of a, or if you prefer, log base 4a equals minus 1. Remember, that means 4 to the power of minus 1 equals a. You can just write that straight away. 4 to the minus 1 equals a. 4 to the power of minus 1 is 1 over 4 to the power of 1. So therefore a equals 1/4. And we're done there.
Question 7 says two variables x and y are connected by the equation y equals kx to the n. The graph of log 5y and log 5x is shown as a straight line. Calculate the values of k and n, and we're obviously given 2 points. So let's start this question. So we've got y equals kx to the n, and we've got the log base 5, so we can log both sides with base 5. So log base 5y equals log base 5kx to the n, which we can separate into 2 separates. Log base 5y equals log base 5x to the n plus log base 5k. Bringing the n down in front, we've got log 5y equals n log 5x plus log 5k. That's a bit like, because it's logarithmic, log base 5x and log base 5y, that's a bit like a big y equals mx plus c. So that's our gradient and that is our y-intercept. So we can work out our gradient because we're given 2 points in the question. Just remind ourselves 0, 3 and 2 minus 1. So our gradient equals minus 1 take away 3 over 2 take away 0. That's minus 4 over 2, which is minus 2. We can then do our y-intercept. That's c, remember. So c was log 5k. That crosses the y-axis at the number 3. So that means that 5 cubed equals k. So 125 equals k. So to answer our question, we had y equals kx to the power of n. So y is 125x to the minus 2, where k equals 125 and n equals minus 2.
This has been Claire Maths. Today we've went through the whole of logarithms in the SQA Higher Maths 2023 exams. Hope you found that helpful and useful. Take care, stay safe, and goodbye.